J. So now if you have any particular row J, and what will be the range of this J? So the range of this J will be equal to 0 is smaller or equal to. So the range of this J will be equal to, it will be equal to 2 to the power A minus M minus 1. So let's assume we have an index J. So let's assume we are enabling a particular row J. So all the chips and that particular row J for a particular address will be enabled. Got it or not got it? So it will be enabled. So let's assume if we have a binary, so we need to convert this J. So we need to convert that J based on the binary of the most significant bits. So the most, okay, here the most significant bits of the address line will be connected or the least significant bits from the microprocessor side. The most significant bits or the least significant bits? The most significant bits. So the most significant bit from the microprocessor side will be connected to the input of the decoder, and the least significant bits, the remaining least significant bits, will be connected where? To the address lines. So now can you see here the least significant bits? So this is the least significant bits. So the least significant bits will be connected to M. So please remember, if we have, now what I'm going to do is I'm going to generalize it. So I'm going to rub this off. Okay, now think. Now let's assume we have A lines. We have, how many lines are there? A lines. Okay, since we have A lines, so can we write it like this? So this will be my what? A minus 1, then A minus 2, A minus 3, and blah 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 until A3, A2, A1, and A0. How many lines are there? A lines. From the microprocessor side. Now we have from the memory side, we have M lines. So we can call it, so this is my address A. Okay, so now basically can you see here? So we have A minus 1, so we have A lines. So we can call it A minus 1, A minus 2, A minus 3. No. Yes, A minus 1, A minus 1, A minus 2. No. Yes, A minus 1, A minus 2, and blah 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 until A1 and A0. And then we have, okay, what I'll do, so I'll explain it from a different perspective. So let's say we have A lines. So we call this as A minus 1, A minus 2, A minus 3, blah 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 until A1 and A0. Then we have M minus 1, M minus 2. Okay, just we have some address lines. Okay, I will now explain it in a more different way. There is a higher ordered bits of the address lines, and these are the lower order bits. Of the address lines. Okay, how many lines will be lower order bits? Can anyone explain? How many lines will be from the lower order bits? Higher order bits and lower order bits. Please remember, we have A is greater than M. A is greater than M. Am I right or not? Since A is greater than M, so this A can be partitioned into A. We have A bits. So can we define something, since A is greater than M, so we define some metric. Let's assume we have K. And K is equal to A minus M. So this positive number which is K, which is actually A minus M. Clear or not clear? So we can partition these bits into higher order bits. What are the higher order bits? Tell me. A minus M. And what are the lower order bits? No, M. If we add all of these two, A minus M plus M, how many bits are there now? A bits. Please remember, I will explain this one in another example. In the example that we did, what was A? A was 21. A was 21 bits. What was M? M was 18 bits, remember? And then we have A minus M, which is 21 minus 18. How many bits were there? 3 bits. So we can partition the microprocessor address into two parts. The higher order parts and the lower order parts. And the higher order parts is what? A minus M. And the lower order part is M. And if you add them, it will result me in A. This higher order A minus M will go where? The input of the decoder. And the lower order M bits will be connected to what? Yes? To the address lines of each memory chip. Clear or not clear? So please remember the same example that we did last time. So just we did it now. So in that case, we had 21 lines. So we had A20, A19, A18. These were the higher order bits. So these were higher order bits. What were these higher order bits? Which was A minus M, which is actually 21 minus 18, which is 23. So these are the higher order A minus M bits will go to the input of the decoder. The lower order bits, A17, A16 and blah 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 until A00. They are connected to what? To the M, which is actually the M address lines of each memory chip. Clear? Any question? Any question? Okay, now what I'm going to do, so I'm going to rub it off and I'm going to explain it here. Okay, so if we have A minus M line, which are the higher order bits, so A minus M line are the higher order bits. And what are the lower order bits? Can anyone tell me? How many bits are there? M. Since there are M lines, so can we start from A0? Then A what? A1 and blah blah blah. Then what? A what? M minus 1. Okay. A M minus 1 will be connected to what? A M minus 1 will be connected to M minus 1 line of each memory chip. A minus 2 will be connected to what? M minus 2 and A1 will be connected to what? M1 and will be connected to what? M0. And in the example that we did last time, we did, okay, what is now M? M is 16. So basically this is what? A17, A16, A15 and blah 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 until A1 and A0. So A0 is connected to M0, A1 is connected to M1 and A16 is connected to M.
M16.
N16 and A17 is connected to? Clear or not clear? Any question? And these higher order bits will go where? To the input of the decoder. And if you have the input of the decoder, so how many outputs are there from the decoder? No. So the inputs to the input to the decoder is A minus M and the output to the decoder is, so now we have a decoder. So the input to the decoder is A minus M bits and the output to the decoder is what? This for A minus M bits. And in addition, we have the address trope which is connected to the enable signal of the decoder. Yes or no? Okay, now this is from the address lines. What about the data lines? If you look at data lines, okay, so now should I write this up? Now I'm going to explain the data line stuff. Because now I'm generalizing the whole concept. I'm not generalizing the whole concept. Okay, so should I write this up? Now look at the data side now. Data side. So if you look at the data side, so please remember, we have D. So can we divide? So we have D. Data lines. Can we divide this D data lines? So can you see? Remember now, we can say now D is greater than W. D is greater than W. Okay. Each chip, okay, each column in this example, each column will provide how many bits? In the example, each column will provide W bits. So how many columns? So we have. Can you see here? So can you see here? So let's assume we have the first. We have, okay. Now we have column 0. Column, okay. Now we have how many columns are there? We have column 1 and then what? Column 2, column 3, and how many columns are there total? Column D divided by W. Each column will provide how many bits? W bits. So this column will provide us W bits. The other column 0 will provide. So this is column 1. So column 1 will provide W bits. Column 2 will provide W bits, and column 3 will provide W bits, and we have D divided by W columns. So can you see here how many columns are there? D divided by W. So each column will provide W bits. This column will also provide W bits. This column will provide W bits, and this column will provide W bits, and this column will provide W bits. How many total bits are there? Yes, can you explain? Let's assume that we have our C columns. We have C columns. Clear? If we have C columns, so now in this case we have column 1, column 2, and column C. We have, what will be the value of C? D divided by W. Okay, so this will be W bits, and W. How many? What will be the total D now? D will be equally CW, and what is now C? D over W, and multiply by W. Cancel out, it will be equal. Clear? So in each column will now provide W bits, and there are C columns. And this C is equal to D divided by W. So the total number of bits that will be provided to the microprocessor is now what? Any question? Okay, I will explain this one another example. Let's assume we have a class and I want to access 8 students at the same time in each row. What is the address of this row? 0. What is the address of this row? 1, 2. Okay. If I am treating only this partition, this partition, how many students can I access at the same time? 4. But I want 8 students. So I need 2 memories. The first memory and the second memory. Okay. What is the size of each row in this section? 4. And what is the size? 4. So in this case, how many columns are there? There are 2 columns. And these 2 columns will be enabled at the same time. So 4 students will be, I can access 4 students from here and 4 students from, and total number of, so what is W here? W is 4. And what is D here? Clear or not clear? Any question? Okay, let's assume we have 4 rows. Row 0, row 1, row 2 and row 3. So what should be the size of the column now? What should be the size of the coder now? No. What should be the size of the coder? Yeah. So we have 2 memory chips. When we have 2 memory chips, you don't need any. You don't need any decoder. Because this is address 0, will provide 4 bits, and clear? Any question? Okay, now what I'm going to do? So I'm going to post one question and now you have to solve it. So let's assume that the main memory requirement one MB and the weight of the address bus on the microprocessor side is 17 bits. The main memory available is 32 kilobyte. Okay, and width of the data bus is now 16 bits on the memory side, the physical memory. Design such a memory system.